it's already
2012 till today, so 12 years.
12 years. Okay, great achievement actually. So just to be aligned with this meeting, I'm going to talk about mechanical responses of disordered solids, and in bulk and in nanoscale. And you will see that I have an ambitious, how to ambitious plan to talk about too many things. I'll give a brief introduction about what I'm going to talk about, and the aspect will be basically shear banding and how to anneal basically material and the glasses, and see what kind of failures that you're going to see in the system. Then, so basically these are plans. So I am going to talk about little bit briefly about how to produce very well annealed glasses using something called swap Monte Carlo methods, and then talk about shear bands. And also then next I will come and discuss about how to tune shear bands using something called microalloying and impurity particles. Then I will talk about briefly again annealing glasses using cyclic shear and what kind of effects it has on yielding processes. And then the fourth one is on along the same line, but using slightly different technique using an active particle, a run and tumble active particle. And I will show it has a fantastic, actually striking similarity with cyclic shear. And if I have time, then I will go into shear band at nanoscales, particularly nano pillars, and I will talk about how geometry affects. And again, if I have time, then I'll briefly talk about memory formation and how a nano pillar can actually store information. So I probably don't have to talk about show you these slides, because I'm sure you have seen these slides in multiple locations. But at least just to briefly tell you that these glasses are there in our everyday life, particularly metallic glass, emulsions, colloids are there in all forms of life, particularly like in paints and then ketchup, glaciers, and makeup materials. But what is more interesting nowadays is the use of these materials at small scales, particularly at nanoscale, because of easy processing of these materials. At small scales, these materials turns out to be a very useful material for fabricating various nano devices, and they have lots of uses. And even for recently there are this micro fuel cell where bulk metallic glass pillars are used, because these pillars will have a large amount of surface area, and the catalysis will be significantly large. But the question that remains is that for this, when you go to such a small scale, is your mechanical property remain very similar to your bulk, or is there significant changes with size reductions? Okay, so I'll briefly discuss that aspect and show how geometry plays important role, particularly at small scale. So this I don't have to really tell you that glasses are one of the strongest materials that one can define and one can obtain, but it has the major problems of catastrophic failure, which is what is known in the physics literature as yielding transitions. Even though we can make very strong materials using glasses and various combinations of these alloys, but how to stop their catastrophic failure is something which is the subject of long debate. And also there are interesting aspects. For example, recent days where you try to basically have a window to see through what is going on in a nuclear reactor. So last December, I went to a center in Kolkata called CGCRI, Center for Glass Research and Glass and Ceramic Research Institute, and where I saw how they actually build to make glasses which are called radiation sealed window for nuclear reactor. And this is very fascinating to know that glass is one of the best option to basically seal the radiation and store the nuclear waste in a safely manner. So there is a significant amount of interest even in that direction. So, but there also one needs to basically understand how to basically stop such fracture processes because they will be under in extreme conditions. Well, why is problem so hard? And this I am giving a physicist perspective. When you try to understand yielding process and deformation in crystals, they are controlled by basically defects. And if you study defect dynamics, that more or less that can be a good tool to understand basically crystal plasticity. But when you talk about amorphous solids, as the whole structure is disordered, it's very hard to define what is defect and then identify and basically study defect dynamics. So, but recently there are significant progresses made even in that direction, and it is sometimes believed that this SLV structures, which are basically quadrupoles, when they appear when you apply various types of deformation, be it simple shear or uniaxial or even uniform expansion. But it's not so easy to talk about these objects as basically non-interacting defects and write down dynamics on those defects. So there are attempts, and one of them is this famous work on shear transformation Jones theory by Langer and the co-workers. And so there are significant progress made along that line, and which suggests that these SLVs, if they line up, then they basically produce shear bands, and that leads to basically crack formations. And it has been shown via energy considerations that SLVs lining up is an energy minimized configuration. This is work done by one of my collaborators from IIT Bombay, Atul Dasgupta, with Itamar Prokachia, my former postdoc advisor. So this suggests that we need microscopic information to understand this plasticity in disordered solids before we actually scale up to study large materials in a coarse-grained length scale. Both are needed, but microscopic informations are essential. And if we can supplement this microscopic information in a large-scale modeling, particularly via finite element modeling, that will be much more closer to reality than what the current scenario is. And so what is stopping us to get a very detailed microscopic understanding of this phenomena is the lack of access to very low energy glassy states. For example, in molecular glasses, you can get glassy state which is accessible in experiment, where the viscosity can be 10 to the 12 or 13. But you do not get the microscopic details of or the arrangements of atoms and their structural information. So some of these can be bypassed if you do experiment, because there you can actually study them and do microscopy, video microscopy, and track individual particles. But the difficulty comes when you basically try to access a very large window for relaxation time or viscosity. So here in colloidal experiment, the largest viscosity change that you can study is order of 10 to the 4 to 10 to the 5. And when you come to basically simulations, there also the biggest difficulty is the time scale. So the largest change in viscosity that one can study is now if you push it a little bit more, it can be 10 to the 5 to 6. So these are very, very similar to what you can achieve in colloidal experiments. So, but in last, I think around 7-8 years time scale, there is a significant change in what we have in basically various numerical techniques, and one of them is the swap Monte Carlo technique that I'm going to briefly talk about. So this is the technique which has been devised at least 10 years or even more, I think 14 years ago by Giorgio Parisi and his PhD student Thomas Briguera. So what they propose is that you do simple Monte Carlo simulations, but you introduce additional step of swapping two different particles and use the same metropolis algorithm to accept those moves. And so this may sound very trivial kind of change in the molecular in the Monte Carlo method, But it turns out this is one of the best way to increase the relaxation process. And I will show some result soon that just by swapping two particles which are of different types, particularly if you, this will be useful only if you are dealing with systems which are binary or polydisperse. For example, in a binary liquids, you can actually take a big and a small particle and swap their positions. And one can easily see the difficulty. So in a dense environment, a smaller particle can easily be replaced on a place of a bigger particle. But the bigger particle cannot be put in the place of a small particle because it is going to overlap with the other particles. So this will be energetically very costly. So that's why the moves will be very, very rare. And if you are dealing with binary mixtures, the acceptance rates sometimes goes in 10 to the minus 5 or 6. But surprisingly, even with that small acceptance rate, the dynamics can be speed up significantly. So this one can actually make progress, and this was I want to give credits to Giorgio. When I was coming back from Rome, he suggested, why don't you try using ternary particles, where you have small, medium, and a large particle, and the swap will be then done on a basically sequential manner. A small and a medium can be exchanged easily, and a medium and a large can be exchanged subsequently. So this will enhance your acceptance rate by a significant amount, and one might be able to basically equilibrate the samples much faster. And so I came back to Hyderabad, and some years went by before I actually took it up, and I discussed this with Itamar, who was my first postdoctoral mentor, and we did this work together. So we actually introduced a ternary model, a ternary glass former, and the model particle size ratios are such, and that this acceptance, swap acceptance rate went up by at least factor of 100. Still the rates are in 10 to the minus 3 or around minus 2 to minus 3, but that itself was large enough to accelerate the dynamics very, very significantly. And we could reach or equilibrate the sample at a temperature where estimated relaxation time can be as large as 10 to the 10 to 12. So this is nearly impossible in using any conventional methods. And so this I'm saying the estimated time scale because this is the place where you do not have an idea about what could be the relaxation time. If you fit data of your high temperature data up to this areas via various forms, the lower estimate turns out to be at least 10 to the 10, which is at least few fold speed up in the dynamics. And using that, we looked at basically various dynamical property and static property, particularly computed correlation length, static correlation length, and found for the first time that a static correlation length in this system can grow by at least factor of 5 or 6, which was impossible to achieve before, and all previous literature data showed static correlation length growing by factor of 2. So this was a significant advancement in terms of how you can access low energy glassy states, which was later picked up in this work, particularly by group of Ludovic Barthier and his collaborators. So they took polydisperse systems where you have a continuous size distribution, and then they basically tune various parameters, including what should be the distribution, the shape of the distribution itself, and were able to tune this the swap efficiency to a scale which is remarkable. And some of their papers, at least in this paper published in PNS, reported the speed up in the order of 10 to the 6. And similar studies done in 2 dimensions, the speed up was achieved to be around 10 to the 10, which is enormous. And it was been claimed that one can reach glassy states, which even with experiment will be nearly impossible. So now with these advances, we are in a phase of glass which can be compared easily directly with an experimental glass at least. And what people looked at is basically they took these glasses, which are called ultra stable glasses, and see them. So I'm basically click the three movies. So extreme left one is for purely annealed glass, and you see that there are a lot of plastic events happening in various parts of the sample. And in the middle one panel is a moderately annealed glass, which you can achieve even with simple molecular dynamic simulations. But on the extreme right, you have an wet annealed glass prepared with a swap Monte Carlo. And you see that, that the plasticity, which is color coded using this non-affine displacement, which I'm not going into details, is very different. Particularly in the poorly annealed glass, you see that plasticity is happening everywhere, and it's kind of a homogeneous yielding process. In a moderately annealed glass, there is some signature of localization of plasticity, but in an wet annealed glass, you see a very, very clean localization of plasticity. And this is what the shear band. So now, even in computer, one can easily generate the shear bands and actually study what kind of what leads to such shear band formations. So there are interesting proposals by the same group is that so this shear banding process in ultra stable glasses are kind of a first order non-equilibrium phase transitions, which has been debated a lot in the literature, and it's not clear what it is. And it's also been claimed that when you anneal or change your annealing history, you are basically going through in a phase diagram where you have a first order phase transition terminating at a second order critical point, and the physics seems to be claimed to be belonging to the same universality class of Ising model in a random field. As I said, these are theoretical development that has been debated strongly, and there are no clear-cut answer yet. It is very, very clear that as one looks at these shear bands and increased system sizes, the stress drop as shown in basically the panel A, it becomes larger and larger. And if you look at the corresponding susceptibility, which talks about how much fluctuations you have around this yielding process, where the shear band appears, that susceptibility turns out to grow with increasing system size. And this somehow signals that there is a large length scale which is coming up, and this length scale is obviously connected to the spanning shear band that one sees. So then we basically asked this question where Pinaki joined. So actually, so this is the work we did 4 years ago with Pinaki, where we tried to look at how to control such shear bands, and can we get a better understanding of what leads to homogeneous to heterogeneous yielding. So this is the work that was published in PRL in 2019. So the concept that we used is this microalloying. So our crude model of microalloying was to actually fix a few particles, and that we call pin particle, and we do it randomly, and this is the reason why this is called random pinning protocol. And using this method, you just basically choose a set of particles randomly and you freeze their position. But when you deform them, then they can move efficiently, but all non-affine motions are suppressed. And we looked at basically yielding process in this kind of scenario. And what we found, which is displayed, I hope you can see my mouse in this panel where we plot stress versus strain. And you see that when you increase the degree of pinning or the pinning concentrations, then basically material becomes much stronger. The modulus here, modulus goes up significantly. The stress peak goes up, but the peak becomes broad as well. And also notice that the yield point shifts to larger strain. So the system actually was able to support much more than basically a non-pinned usual glasses. And when we looked at basically the spatial map of plasticity, we see that when you do not have any pin particle, then you get this low panel data set or the maps where you get basically clear shear band type behavior. But when you have some amount of pinning in the system, then you get an homogeneous yielding. So this is signified by this stress peak, which is broad. So this random pinning is not a very ad hoc thing because it's also been experimentally realized in a group of Rajesh Ganapati and Ajay Sood. So they were able to do laser trapping and looked at various dynamical and mechanical properties of this pin system. So there is a very large literature which actually started from this direction. So then the next question that we had in mind, how to do microalloying, which will be applicable even in, let's say, in experiment, because this kind of random pinning will be impossible to achieve. This is doable in colloidal experiment, but not in molecular experiments. So we propose that if we actually introduce particles which are bigger in size, then this big particle will have basically relaxation which are times which are much larger than your host. So they will have much smaller diffusion coefficient than the medium particle. And over a time scale of the medium relaxation time, this particle can behave as like a soft pin particle. So we tried this concept and studied the yielding process in a setup where you introduce particles which are twice the size of your host particle. So this is signified or demonstrated in this figure in the right top left corner. So we took basically particles which are of diameter twice, and we looked and we just basically change their concentration. We do see that the yield point moves to larger strength, and so it has some pinning like effect, but it's not fully what you can get it in a random pinning. But it produces some effects which we feel is a signature of a pinning like effect. And then we went on with the idea, instead of basically using a large particle, we thought of introducing an elongated particle and to see whether they can be better pinning sites, because a long particle will have various dynamical restriction in terms of both translation and rotation. Particularly in rotation, they won't be able to rotate as freely as a spherical particle. So this is what we looked at in this scenario. We basically took a system and introduced dimers. And the dimers, when you increase their concentrations, then what we see is that when you have the zero basically dimer concentration, then you get usual stress strain curve, which is represented by this brown symbols in panel B. And then you gradually introduce your dimer concentration at for large enough dimer concentration, which is around 10%. Then you see that your material becomes much more strong in terms of enhanced shear modulus, and also the peak position moved significantly. So your yielding has been delayed a very significant amount. So these systems are able to support loads by a large amount. Sorry. And if we compute the susceptibility, so it turns out the susceptibility peak increases very rapidly with increasing number of dimer concentration. So that is signaling some sort of shear band formation. And indeed, when we look at the spatial map in terms of this non-affine displacement, we see that already in the samples you start to have some shear band. But major achievement in this dimer simulation was that the yield point could be shifted by significant amount. So then, to just for sake of theoretical curiosity, so what student did, he stopped the rotational degrees of freedom of these dimers. So the dimers in the simulation can no longer rotate, so they are frozen by hand. So if you do it and then look at the same stress strain curve, then we see that the stress strain curve becomes very different. Now it becomes the yielding becomes extremely sharp, which is signaled by the susceptibility. The susceptibility peak went by at least 10 to the 4, factor of 10 to the 4, which is huge, which tells us that the rotational degrees of freedom of these dimers are extremely important for promoting or stopping this CR band formation. So what it does when they cannot rotate, so they somehow concentrate all the strain or localize all the strain to form CR bands. So which you can see in this snapshot. So when you have some amount of dimers, then you have some CR band, but CR band is somewhat diffuse in the sense that it is not, so the width is significantly large. But if you increase the dimer concentrations to at least 5% or 10%, then the width, the CR band becomes extremely narrow. And that is also signaled by a very sharp stress drop in panel C, which is, so this was supposed to be A, but I have taken it from the paper itself, and it's a cut and paste problem. Sorry for this. So this gave us this crucial hint that if you try to microalloy materials to improve their material property, particularly the modulus, and then this elongated particles can be good choice because the modulus increased by a very significant amount. But it also promotes CR bands if because of their rotational hindrance. So in these simulations, the rotation was frozen by hand, but in reality, if you need CR band to be present in your system, that you can achieve by introducing long rods. So if you increase your impurity rod length systematically, then what we found is that you can indeed achieve the same scenario what we achieved when you basically freeze the rotational degrees of the rod particles. A long rod obviously stops. Long rod will have very large hindrance for rotation, and they lead to very clean CR band formations.
There's a question, Shorajit.
Yeah. Yes.
Yeah, so the susceptibility is just an overlap function, right?
Susceptibility is, so you basically compute the standard deviation of that overlap function.
Overlap function. And if you have like plus kind of particles, I mean, will it hinder the rotation instead of just
the plus, if you have that kind of particle, we haven't looked at, but they may be a good choice because they also have rotational difficulties as well. But whether they will localize CR band or they will diffuse it is something which I don't know. It looks like promoting CR bands in a particular region. But also note that in this snapshots, rods are actually distributed everywhere. It's not that they are all aligned in the CR band. But somehow their presence leads to much sharper CR band formation.
Yeah. Are these shear bands devoid of those the elongated rods?
No, they are uniformly everywhere.
Okay.
It's not that their concentration increase in the CR band.
Right.
It's not the scenario. They are still uniformly distributed in the sample, but somehow CR band are much thinner.
Do you allow them to, when you shear the sample, do you allow them to move or not move? I mean, I understand about the
in this scenario, they are free to do both rotation and translation. But just because they are elongated, their rotations are hindered very, very significantly.
Okay, their aspect ratios are
so here the aspect ratio is around 2.5. It's not very long, but I think 2.5 particle diameter.
Oh. Thanks.
So then we wanted to actually do some structural analysis, and this is so we took up this work of Hajime Tanaka, who looked at basically how the particles are packed in various local regions, and this is this Tanaka order parameter, which basically looks at in 2D the angles of your nearby particles and the distance, and then you can compute that order parameter. In 3D, you basically look at the tetrahedrons around the particle. And when we basically introduce rods, and if you increase the rod length, then it turns out the Tanaka order parameter decreases significantly. So smaller value of the order parameter means that you are much more stable. So larger value of the Tanaka order parameter will lead to more disorder in the sample, or basically loose areas. So this rod somehow helped us to achieve something which is very pinning-like. Pinning also makes your sample become much more ultra-stable in that sense, or by increasing CR modulus. And the rod seems to be doing something very similar. So we also compared the amount of, or the degree of structural ordering in this, or I should not call structural ordering, structural stability compared to ultra-stable glasses. And it seems that this elongated rod and their concentrations can give you a glass whose stability is somewhat comparable to this ultra-stable glasses using swap Monte Carlo. So this is an interesting way to achieve stable glasses. Although we could not stop CR bands, so sometimes basically the CR bands are promoted, but the yielding process is delayed. So this has this good one good advantage is that the modulus goes up if you increase the amount of long rods, and your yield will happen at a large speed. But when it happens, it will happen in a catastrophic manner. So the shear band something which we could not stop or diffuse. So this is though it has some pinning-like effect, but it's not similar to what pinning does. So if you then look at basically the shear band and then cut through the profile itself, and you see that the order parameter is very large in the shear band region. And interestingly, outside the shear band, the order parameter is much smaller than your undeformed sample. So whatever the average order structural order parameter of the sample, but and if you compare the same structural order parameter in a non-banded region, they turn out to be smaller than your undeformed sample, which telling us that somehow the non-banded regions became structurally much more stable, which is a surprise for us, and we don't have an answer to it. And hopefully in future we'll be able to get a good understanding by doing a better structural analysis of this, both the banded and the non-banded regions, because producing the shear bands are now is much easier for us than in computer. And and we also looked at basically if you cool your sample at a different rate, which is basically defined by this parent temperature T. If you basically go to very low temperature and then you cool, versus if you take a high temperature liquid and cool, so that will give you a different cooling rate in some sense. And you do it if you prepare your glass from a high temperature liquid, then you get a shear band which is much more diffuse. But if you get it in a well quenched glass, that will have a shear band which is significantly narrow. And so with this kind of basically framework, we are planning to study how the shear band width increases as you basically deform further after the shear band forms. And what are the other parameters which controls this shear band width? And what is the scale that appears here? So is there a natural scale that that controls the thickness of the shear band? Some of these questions are not clear to us, and hopefully we'll have an answer in the near future. So this part maybe you can, so this is a detailed structural analysis or structure around the rod itself, and I'm going to skip this part. So if we do not have any questions from the previous section, then I want to move into an interesting story of annealing using an oscillatory shear protocol. Okay, so I'm just assuming that there is no question because I have only a few minutes left. So in oscillatory shear protocol, what you do, you basically take a sample and shear back and forth in both positive and negative directions. And this has been shown that this leads to annealing of your material. It helps rejuvenating the sample. And so if you look at this figure, I hope you can see my cursor, and or I can use laser pointer. So this figure, so here it was schematically shown the average energy as a function of this oscillatory shear cycle. And if you start with a poorly annealed glass, then you can actually anneal the sample very well up to a point, and after that it heals. So, and then there is an interesting energy scale. If you start your oscillatory sphere below that energy scale, then it turns out that you no longer can anneal the sample using this oscillatory sphere protocol. So this energy scale turns out to have a very close correspondence with what an MCT energy scale is going to be. And why it is so that we do not have an answer, or not the others who have worked on this as an answer to. But what we looked at in addition is that instead of doing an oscillatory sphere along one direction, let's say in XY plane, we introduced oscillatory sphere along other possible directions. Particularly in a 3D, you can have XY sphere and you can have YZ and a ZX. Okay, and what we found that if you do an XY oscillatory cycle, then the energy reaches a steady state. Then you switch your direction and do YZ, then the energy decays once more and reach a plateau. And from there, if you do XZ oscillatory sphere, then you can further annihilate. And you can actually have various combination of this. You can do X, Y, Z, and then repeat the same pattern, or you can have X, Y twice, and then YZ and XZ, and then repeat that pattern. So depending on what kind of pattern you want to choose, the steady state or the absorption state that you get turns out to be very interesting. For example, you see this panel where if you do unidirectional oscillatory sphere on XY plane, then you get a steady state which has only one energy scale. But if you do oscillatory sphere in 3 directions, then you can reach a steady state which toggles through 3 energy states, which is very interesting in the sense that which I may come back if I have time. That these states, state store memories. So if you do multiple direction oscillatory sphere, there are possibilities that you may be able to store multiple memories along those directions, which is not yet achieved, but the possibility still holds. But what is most important and interesting is that the better annealing procedures, although the phase diagram remain very, very similar. So there also you have an energy scale below which you can no longer anneal your sample using oscillatory sphere protocol. So mechanical annealing seems to have a lower bound. So this lower bound is a fundamental question which, as I said, that nobody has an answer to, and which remained as an open question. And so one interesting thing that we found is that if you do a random sequence of oscillatory sphere, then your energy profile goes down, 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 and it takes enormously large number of cycles to reach a steady state. Okay, but so this tries to explore various complex paths of the minimus, and then eventually will saturate at some point because the phase diagram doesn't evolve beyond this. So this oscillatory cycle has an interesting basically side effect, and in some sense the question that we asked is that so we know that there are various types of glass forming liquids. So some glasses are strong liquids, some are fragile liquids. So we asked this question, are the same in terms of yielding process? Okay, so in this figure we have taken a system where basically the kinetic fragility can be tuned systematically by changing only density, nothing else. So this is a mixture of a 50-50 binary mixture of harmonic spheres. At densities, let's say for example 0.681, you get basically a state which is more strong light. And then this state you can take and cool it to go to 0 temperature glass and look at their dynamical property. But if you take a density which is 0.943, which is this black stars, then you get a very fragile liquid, and you can actually quench this liquid to get a glass former generated from these fragile glasses. So we repeated this same oscillatory sphere in these samples, and for the strong case, what we found is this the phase diagram or the annealing property changes significantly. So one interesting point which we have is that if you start from poorly annealed, then your annealing goes on and on and on. At some point it stops, And beyond this yielding, beyond this oscillatory amplitude, then you start to basically yield, and there is no longer any annealing. But the point at which you yield remain very similar, even if you increase your annealing. If you go to lower and lower energy state or better annealed glasses, your yield point do not shift. At the same time, if you look at glasses formed using this from these fragile liquids, which is this density 0.943, and look at the same phase diagram as a function of the oscillatory shear amplitude, what we see is that the yield point moves significantly with increasing annealing. So as you go to lower and lower energy state, your yield happens typically with a shear band formation, but at a strain which is much larger than what you get it in the poorly annealed glass. So this physics, it was something, at least for us, it was somewhat surprising. And because strong and fragile concepts are typically useful when you are dealing with liquids, not when you are dealing with an amorphous solids. There you are talking about brittle or ductile behavior, and which we feel is related to your annealing protocol. But the changes in the oscillatory phase diagram for a strong and a fragile glass forming liquid, when you basically generate glasses from them, and this difference was surprising. And then we asked this question: is there a way to understand it? And what we feel is the scenario lies in the shear band. So if you plot stress versus the strain, then what you see that in a strong glass, even if you have reasonably well annealed glasses, you still do not get very clear-cut shear band-like drops. But for a fragile glass, you get a very clean shear band formation. And so we are pushing ourselves a bit more along this line, and we have to basically simulate much larger system size to get a clean shear band and to study whether indeed the strong glass former versus fragile glass former, there is a difference in the shear band, and we don't have an answer to it yet. But these observations can be actually explained if you basically do some sort of a mean field calculation of this. So this mean field modeling was first proposed by many people, and then subsequently Srikant proposed a new single site model, which is a single site model for an amorphous solid and yielding behavior. So the idea is that you can actually think of the amorphous whole solid being moving in various energy landscape. For example, you at zero strain, you are in this energy landscape. This is given by this black card. And as you strain the sample, then the system goes up in this energy landscape and then topples to new energy minima. So maybe this one, but if you do a reverse shear, then you can actually access this red minima. And so if you basically put a few such rules, then more or less you can actually reproduce all this oscillatory shear diagram of an amorphous solid. But what was missing in this thing was the difference that one might get if you take a fragile versus a strong glass forming liquid. And what we feel, the answer in the fact of how energy barrier changes in these two types of liquids. And then when you basically generate glasses from them. For example, strong liquids has been shown by explicit calculations. The typical energy barrier cooling history does not change. Okay, even if it is it changes at when you are in the poorly annealed regime, but you go to well annealed glass regime, then it's more or less saturated here. So this is represented by this blue card. And if you have basically very fragile glasses, then energy barrier grows strongly with your basically annealing protocol or your temperature. And to use this information in this mean field single site model and repeat the calculation to produce the steady state of oscillatory shear, we find that when you basically take a liquid whose band doesn't grow beyond a certain value as you do better and better annealing, you get a diagram where the yield point do not move anymore. But if you take a glass which is modeled by this black curve where the energy barrier grows with annealing history, then you get a phase diagram where you can clearly see that the yield point systematically moves to higher and higher strain. This suggests that while modeling this kind of materials at a coarse grain length scale, one must include these informations of barriers and how they evolve with basically your annealing protocol. And so although this is a single site model, so the talking about chip band in this is nearly impossible. So we have a joint work with Pinaki, Viswas and Siladitya, which we are trying to develop and do a multi-site model. And we believe that that model will be able to reproduce the differences in shear bands if we see something here.
Sharojit, your time is almost up,
Yes.
so you can finish fast.
Time is almost up, okay.
Yeah.
So then I will actually, I will take 2 minutes and talk about the size effect,
Sure.
and then I can stop and take questions. So now I will give you a brief, basically show you some results which we have when you basically go to nanoscales. And this is in the literature there for quite some time, which said that if you take nano pillars and deform it, then if the pillar diameters are smaller than around 100 or nanometer or so, then you get deformation which is more homogeneous, like this bulging type phenomena. But if your samples are thicker, then you can get very clean shear bands. And this is something similar has been shown in this paper as well. As you go to very, very small nano basically pillars and pull them and a metallic glasses, then you can get basically shear bands, again, very, very thin neck formation. So we looked at something similar in our simulations. So these are the basically pillars which are annealed using active particles, or you can also anneal them by oscillatory shear. And I did not talk about it in details. But if you take this system, so aspect ratio is 1. So basically, it's a cubic pillar, and then you pull it, and then you see the shear bands are not very clean. But if you take a pillar which is size of aspect ratio is 2, height versus the base, then you get a shear band which is somewhat is much cleaner than the cubic one. But if you take an aspect ratio which is close to 4, then you get a very clean shear band. And if you look at the corresponding stress strain curve, then you see a very sharp drop. It suggests that it's along with annealing protocol, as you go to an open geometry scenario, your sample geometry is going to start to matter to give you the stability. So just to stress on the geometry, we looked at not the sample size. So we looked at bigger system size, 64,000 particles, but in a cubic shape, and you see that there is no shear band. But if you take a smaller system size of 32,000 particle simulation, but with an aspect ratio which is 4, then you get a very clean shear band. So this tells us that sample but smaller aspect ratio, you are going to get less shear band formation. But a smaller sample but an elongated geometry will have much more shear band. So that's why the pillars, when you basically use for any practical purposes, one has to be careful about the stability, because they can fail catastrophically as well. So maybe I stop here, or because I had a couple of slides to talk about memory formation, but maybe I'll skip that part because it requires some discussion as well. So I will stop here and then highlight the funding. Otherwise, they are going to raise the objection. So the research that I carried out was funded primarily from my institute at TIFR, and the money came from Department of Atomic Energy under this project. And I have a couple of basically government money from Science and Engineering Board by this core research grant, and I got fellowships and Sanjay Jansi fellowship money. This has been used for doing this research. And thanks for your attention, and we can have some questions.
Let's thank the speaker. Thank you, Sharojit, for coming to and presenting the talk. So, few questions we can have. Questions.
Yeah, Sharjit, I had a question. I have a question.
Yes.
For this, like, you are annealing in different directions, right? I mean, you are annealing by oscillatory shear, by shearing it in different directions, oscillatory shear.
Yes.
So what is the typical, like, strain amplitude that you use to anneal them?
So this system that we studied has a yield strain at around 0.07. But and we basically vary the yield, the strain amplitude from 0.01, 0.02, 0.03 up to 0.06. And if you go beyond, then you do not get any annealing. You basically yield.
No, I'm not talking about annealing. I'm still talking about those energy, like, things that you showed. And the strain values,
So
can you go back to that?
So I'll go back and just show me which one.
The oscillatory one in different directions. X, Y, and then you're doing it in different directions.
Okay, just yeah, you just go back. Here?
Yeah. So what are the strain amplitudes for these energy plots that you are making? There is like it's a
so these are all done with I think 0.01 or 0.02 probably.
0.02. And what is the yield point for
Yeah.
that?
This is again a yield point is at 0.07 in 2D, and the same model is being studied in 3D. Okay. So there it was 0.09.
Okay. Yeah. Thanks, Amin.
So what is interesting is this nice plateau appearing. If you basically shear it along one direction, then it saturates there.
Certainly, yeah.
Then again, if you do it in other direction, then you again have a cascade of events and leading to a new minima. Yeah. And this minima, this structure continues. Yeah. So there is some sort of a compactification, which plotted in this figure, where you can see that the average energy as a function of number of basically changes in this direction. That's like a compactification process. That decays as 1 over n, which is somewhat reminiscent for to granular matter. Yeah. If you look at basically they have this compactification in granular matter. Yes. So there you can compute basically changes in volume or increase in density, which seems to show similar 1 over n behavior. And so we have no answer, no microscopic understanding of it, but this seems to have similar behavior.
Thanks, Shurji.
So there is question from Professor Jordi Ortin.
Thank you.
Yes, yeah.
It's just a curiosity. I'm not acquainted with this field, but the two transparencies that you could not show us about encoding memory, I just wanted to know whether memory is encoded in the atomic positions at the end of the cycles, or is some other encoding that you are talking about?
Okay. Let me let's go there. This one. So this atomic. So we computed using this mean square displacement, and this is not in the. So it's not exactly. See, you are asking this question: if I come back, am I exactly coming back to the same configuration, to an atomic precision?
Yes, this is what I would like to know. Yes.
Yeah, I think I don't think we are coming back to that kind of a precision. We haven't explored it, but do you have any insight of why you think that it's not going to come back? The energy is very, very similar, at least to the machine precision that we have.
No, I have no idea. I'm just asking.
No, I think so there are various works done which suggest that there are connected minima where the system moves around. And the interesting thing, if you give me 1 minute, which is in the next slide. So here the interesting point was that if you do multi-directional oscillatory shear, then you can read in any protocol you choose, the memory is not going to be erased. But if you do it in one direction and mistakenly read in the opposite direction, then you can actually erase the memory.
Okay, that's very interesting. Yes.
Yeah, so this is what we showed. So if you, let's say, if you do XY is here to code the memory, and then you do an orthogonal XZ mistakenly, then you actually have erased the memory and could not recover it.
I understand.
But if I do XY, YZ, ZX and then reach and store the memory, then I can do any one of the methods and I will have the same information without basically losing it.
But is the information...
Yes.
Is the information encoded in the position of the particles at the end of each cycle?
Probably not. This is like somewhat coarse-grained and computed using mean square average mean square displacement. So it's probably not of that scale.
Okay.
So you're saying
Yeah.
the
So-
memory is encoded in the
Yeah.
energy values, but not in the positions of.
The atoms.
Yeah, I think it definitely goes to some sort of minima which are somewhat nearby and similar energy scale, and not too far from each other, but probably not exactly the same minima in a mathematical sense, in a precision which is machine precision, for example.
Just
It's
one-
not the case.
If I ask you a question like along the same line, so let's say I do the same experiment with colloids. Can you point to me a good quantity to say that the system comes back to the same memory because all that I have is positions of the particles.
So I think you can actually do compute this mean square displacement from your initial sample.
Okay.
So with respect to that, if you compute it, then you will see that you can actually get the signature of the memory in the mean square displacement.
Okay.
So for example, if you have Sayantan probably showed that this is also encoded in modulus. If you can compute local moduluses, then also modulus shows a change at that strain amplitude.
Okay.
So those are much more global quantities, and they do have that information.
Okay.
Thank you.
Any further question? If not, then let's thank Professor Karmakar once again, Sharajit. Thank you very much.
Thank you. Thank you. And thanks for the attention and these nice, interesting questions.
Thank you.
I will stop sharing so that Stefan can share
Yes,
now.
I think so. Yes. Thank you. So our next speaker is Professor Stefan Luding from University Twente. Stefan, yes, you are there. Yeah. Yeah, hello.
Hello.
Good
Hello, everyone.
afternoon. You can upload the slides.
Let's hope it works.
Yeah.
No, that's the wrong screen. 1 second. Okay, I can do it also here. Can you see my screen, full screen?
Absolutely. You can just wait for 1 minute,
Yes, sure.
Yeah. I will tell you when to start. Thank you. Yes, Stephen, you can start now. Thank you.
Thank you.
Yeah.
Okay, so thanks everybody. I would like to be with you, but unfortunately I only can join online. So here is my online presentation. As you will see in 2-3 minutes, it's slightly experimental, so let's hope it works. Now, the talk is about granular matter upscaling, and I will show you some steady-state results, some more new elastoplastic results on granular matter, also on transitions, and I will go to mesostochastic events, and I will explain you what I mean with that. Before I do this, I want to say some words about keywords or nomenclature. and also to avoid confusion with the previous talk. Okay, maybe not confusion. The previous speaker was evidently talking about things like aging or memory and so on. I also will talk about similar things, but sometimes I will use different words. So I want to just quickly throw some words at you, such that you are not too shocked when I say something which is not exactly in the same language as the previous speaker. So sorry for, I will create confusion probably. Now, in rheology, you have words like viscoelastic, elastoplastic, thermoviscous, mobility, aging dynamics, relaxation times, and you think of polymer melts, for example, and many other materials. Now, I will use mostly words like solid-like and fluid-like, because that's in the granular community used, but that is related to the keywords from rheology. Sometimes I will say something about elastoplastic plus viscous plus thermal things in theory or numerical context. I will talk about transient dynamics, or at least I will try to get there. Okay, so, and there are other keywords which I will use. Stochastic, I will have to explain what I mean with that. Thermodynamics, I am not claiming that I do non-equilibrium thermodynamics, but the systems I'm talking about are not in equilibrium typically. And upscaling is also related to nanoparticles, microparticles, mesoparticles, but the context will become more clear. I will not only refer to particles, I will refer to different scales of observation. Okay, and I will, in some part of my talk about work, heat, entropy, which are very classical concepts. And as I mentioned already, solid-like, fluid-like. I want to go beyond the classical concepts, and granular materials, in my opinion, are already beyond, so we only have to understand them, and then we are beyond, whatever that means. And something like a granular thermodynamics with a question mark, so you will see. Now, the overview of my talk, I have two parts. The first part actually is recorded, and I do this for the first time. So I don't know if you want to stop me and ask questions during the recording. I'm not sure whether that will work, so maybe you keep your questions for later. Because in the second half hour, I'm surely happy to take any questions, and also interactively, I want to focus on one or two of the items which are mentioned in the first recorded part. So the experimental thing is the recording, which should start now, and then for 28 minutes or so I will not talk interactively, but I'm ready to take urgent questions if there are. Otherwise, please wait a little bit longer, and I'm surely happy to take questions later. So let's hope the recording starts now and is working. If not, I will just continue without recording, but the recording should start now. Thank you for the invitation, and unfortunately I cannot attend physically. I miss you all very much, but I hope you can at least see my recording of my plenary talk. The talk is about steady-state flow rheology, that's the first part, and elastoplastic transitions and mesostochastic events, that is the more recent results which we have got in the last few years. So the question is, why are granular materials interesting? Now, from the natural science point of view, physics related, they are interesting because they can exhibit liquid phase, gas-like phases like in a sandstorm, and solid phases like on the beach when you can walk on them. Now, how do we approach this system? How do we do the micro-macro transition? So first we take a look at particles, and for the particles we have to define the contact model. Then the discrete particle model or the discrete element simulation contains the contact information, the particle information. Then you can simulate many particles, for example, like here flowing down a tube, flowing down on a slide. Okay, and on the bulk scale, the real macroscopic world, that is the world of continuum models. How can we go from a particle, many particle model to a continuum model? And if we have this, then we can solve real avalanche problems, for example, on the macro, on the continuum scale, starting from the smaller many particle system and starting from the microscopic or nanoscopic contact models. If we have a micro-macro transition like this, we can change the contact model and can see how that changes the macroscopic scale. So, how to do this? How to approach this? First, let's take a look at the microscale and translate information from the local particles to the continuum scale, to the macro scale. The first example I show you is a silo flow, and here you see particles, they are flowing down, here's the outlet, and we can evaluate the system information at different points, or we just can view the fields in the whole system. Now, for fields like density, this is how density looks like. The density is lower in the shear bands than at the outlet. This is momentum density, momentum or velocity. The velocity is highest close to the outlet, and it gets down to very small values in the stagnant zones. Okay, and then we have strain, which is non-symmetric. The different colors left and right tell you it's non-symmetric. Now, for the rest of the talk, I have 2 parts. First one is steady-state rheology, and the second one is about fluctuations, elastic plasticity, and mesoscale events, which I will explain later. Now, after we have done this, next thing is to deduce non-Newtonian rheology, constitutive relations. Now, more general, the mu of I rheology represents the orange line. That is the critical state, the steady state flow when a fluid remains a fluid because it's driven and sheared all the time. Now, but there are also other things which are interesting. When you start from a stagnant, solid-like state and you start shearing, then you will reach a yield locus and the solid will become fluid. Or when you are in the fluid critical state, and you stop and relax, then the fluid will become a solid. So these transitions are also very important subjects of our research. In the steady state, which is the main focus today, we know now how to translate information from local particles to continuum and how to deduce some type of materials rheology. But what if we have dry materials? What if we have frictional materials? What with different friction coefficients? What if we have cohesive materials or wet? Now, how to do that? So, worked on this, and a simulation, a zoom into the system allows me to display what we are doing. So blue are particles at rest, red are particles which are moving with the outer wall, and green is where the shear band is. The array here tells us where do we evaluate the data, and this gives us a set of shear rates, shear stress, normal stress, density, and others. Information on every point of the system, on every of these grid areas. Okay. And with this, we can plot constitutive relations. So, for example, shear stress against pressure. All the data with a moderate shear rate or larger collapse on this friction law, on this Coulomb-like constitutive relation, which is the straight line. Okay, and the slope, that is the macroscopic friction. However, when we plot shear stress against normal stress, here we do it with units, then we see that increasing friction, particle contact friction coefficients, give us an increasing slope of this friction law, this mu of I law. Okay, and this is the slopes plotted against the particle friction coefficient. So it's increasing and then it's saturating. Okay, this is what we can get easily out of it. Now, given a set of simulations of different materials, which material parameters match with the experiment? Okay, so here you see experimental data of shear stress versus normal stress, different materials, different particle sizes in this case, different cohesivity, and actually also different devices, FT4 and ring shear system. Now, given the experimental data, we can match the simulation parameters to match the experimental data, that is called calibration, or given a set of numerical material, we can find experiments which validate the simulation. So we can do both. Okay, now, for rigid particles, there's an effective strain rate. I is the non-dimensional strain rate, I come back to that one, and the bulk friction follows the mu of I rheology for many different simulations. Different colors are different simulations with different situation, different global shear rates. The coordination number, the particle contact number, is also following a trend, but it's more complicated. There's this zigzag structure here, but they follow a trend also. I will not talk about coordination number today in detail. Now, for the macro friction, the solid line is well fitted up to a certain extent by a linear function in I, where alpha is almost 1. Okay, so constant plus a linear function in I. Note the logarithmic axis here. Now, what happens if I do not only change the shear rate, but I also change the stiffness or gravity? It gives me no data collapse to begin with, but if I find a right dimensionless combination, then the data actually do collapse. I can also rewrite this a bit, express it as dimensionless stress, and then the collapse data for many different simulations follow also a trend, and the friction is actually going down. The bulk friction is going down with the non-dimensional stress. They are collapsing, but the trend is qualitatively different. And this looks like constant minus function of pressure, dimensionless pressure, to the power beta. And here beta is 0.5. So in my definition is we take the additive thing, but we replace it by a multiplicative thing, because that's much more handy. And the additive terms come out from the multiplication, but there's also a nonlinear term popping up, which actually is hard to quantitatively deduce from particle simulations, but actually might be there. And then the multiplicative rheology has the advantage that it's directly involved. Okay, now anyway, each of these linear terms is linear, yes. Each of these first order terms here is linear, actually linear in time scales, not in pressure. Okay, and the nonlinear term definitely is not linear, but we have a first order linear model this way. We did this in 2015 and later in 2017. What if we have cohesive particles? We have another correction, which we constant, add to the constant as a linear and actually a quadratic term in the bond number. And all these terms are, almost all of them, except the bond number term, all of them are linear to first order. Now, as a summary of my presentation, I talked about steady-state flow rheology. We have a micro-macro-based constitutive model based on inhomogeneous DEM simulation. And we could present a rheology which is quite general in quite some material properties. Micro-macro allows us to predict the macro flow behavior, and this can be used in continuum solvers. And the corrections are all formulated in dimensionless numbers, ratios of timescales here. And in general, all of them are needed, and all of them appear linear to first order. Thank you. Now, for the second part of the talk, it's more about steady state. It's about fluctuations and steady state. It's about transients. It's about rate dependence, and it's about mesostochastic events. Some of these things are being addressed in the second part of the talk, some of them are too much. Consider shear stress versus shear strain. So the difference between shear stress and shear strain. And the blue line is shear from isotropic state during a certain time with a relatively slow rate. Now, what happens during shear is that you have elastic regimes and you have elastic events. So there's a mix between elasticity and plasticity. In this resolution, you cannot see it. I will zoom in data. Okay, but in this stress strain picture, we can analyze all the fluctuations. Okay, how do we do this? So we take the probability for stress going up, we take the probability for stress going down, that's on the horizontal axis here. Delta sigma being positive or negative, means your stress will increasing or decreasing. And the delta epsilon is the range which we look forward. Okay, so if we use a small range, we get a narrow Gaussian distribution, it's almost random. If we use the wider range, then we get something which is not Gaussian anymore. It's actually too peaked, and it's not symmetric left and right. Okay, so that's for larger delta epsilon than the Now, if you do the statistics a little bit more detailed and so on, and better statistics, then you get the probability, and you see the yellow distribution. It's not centered around zero, it's slightly positive, that's the elastic division, and it's plastic on the negative side, and it's highly asymmetric. So the probability for elastic events is exponentially decreasing, so that's normal statistics. On the left-hand side, you have the possibility for rare events. So we have low probability for big stress drops. Okay, and that is special. So keep this picture in memory, you can correct it. The two plots, one plot is hidden by my face. The two plots are just different densities. It's qualitatively the same. The details at low density, high density are different. Okay, but what is important is we have a probability for elastic events, stress increase, delta shear stress. Shear stress changes proportional to shear strength on the right hand side. Negative are stress drops, and what those are, we'll explain later. Okay, so this is the statistics about the fluctuations. R is continuum. I did not yet bring in the rate dependence, and I introduced the probability for events, so elastic behavior and plastic stress drop events. So what is going on? The evolution of stress, the fluctuations which you saw, the statistics, under any type of deformation. I only showed you shear so far. Under any type of deformations, there are two possibilities: elastic, and that's what I call reversible events, elastic stress changes, they will be reversible by definition, and plastic, and they will be irreversible. In order to understand what is going on in a stress-strain situation, left plot is stress-strain, as we saw it before. We want to analyze it. So we have a MATLAB script which is taking all the stress drops and numbering them, and then we can do statistics based on the stress drops. So in the left plot you see stress-strain, as we had before. In the right plot you see delta stress over delta strain, which gives us the elastic shear modulus. That's the horizontal level here. It gives us the stress drops which are going negatives, and it gives us a few rare events which are going slightly positive, at least for a short time. So that are stress jumps, but they are very rare. Stress drops are the normal thing which are happening, and they are happening at different magnitudes at this point. Now, when you do the analysis, you get a lot of data, a lot of statistics, and then you want to clean up and plot a histogram which involves the jumps, the drops, and the big drops. And we want to understand whether the small drops are really relevant, whether the big drops are more relevant. The big drops are the interesting ones, by the way. A lot is going on. Okay, and then we can do statistics, and we get something like average change in stress, average change in modulus, and some other things, as you will see on the next slide. This is now the zoom into one event. We are looking at stress, we are looking at modulus, we are looking at kinetic energy, and we are looking at coordination number. At the top left, you see the shear stress. That's the orange line, and there's the stress drop, shear stress drop. The blue line is the hydrostatic stress. Actually, there's a little bit going on, but not much. Only a wiggle, no drop. Okay, so hydrostatic stress and shear stress are qualitatively behaving differently for this event. This is the modulus, delta stress over delta epsilon. And the modulus doesn't change too much. There's a drop. The modulus is not active. The material has no elastic stiffness during the event. And then it goes back to almost the same level. Kinetic energy is bottom left. So here, at the event, at that what we identify as the event, kinetic energy is going up, and then it's shooting up after the event even much more, and then it's exponentially decay. So this is one of the event kinetic energy going up by orders of magnitude and then going down again. And the plateau, this is the elastic area, and the event where the particles are moving around and rearranging, this is that what I referred to as plastic, as irreversible before. So you can go from here before the event to another point before the event and back, that's reversible. When you go from before the event to after the event, you cannot go back. This is irreversible. Okay, and finally we look at the coordination number sometimes. Here not much is happening, but there are much more violent events where the microstructure, the contact network is changing number a lot. So in summary, what we learned from our particle simulations, and I didn't make that clear yet, only if you really go slow, very, very slow, then we can identify these isolated events. Isolated events are plastic, irreversible, and they interrupt the reversible elastic base state. Okay, and for this one, you really have to go slow enough. Most of the time in finite size systems, experiments, you have too many particles and you cannot go that slow. In simulations with small system size, a few thousand particles, 10,000, 20,000 particles, we can go slow enough, we have to be patient, but then we can distinguish the stochastic plastic events which interrupt the reversible elastic state. Now, there is a special case, and that is when you have an unjammed system and you shear and the system jams, as was presented by particle simulations by Viscofi et al. A few years ago, and we made the theory for this, which gives density and coordination number and pressure, all the continuing quantities, and the red arrow indicates the jamming event. So there is a possibility that you have an unjammed system, you shear, and you jam the system. In simulations, it's the green line. In theory, it's the blue line with the marker. Now, this is the animation of such a shear event. It's a special situation. You go from unjammed to jammed in a volume-conserving shear system. And actually, you can go cyclic shearing. You can go shear forward, backward, but I won't show too much of this. Okay, now the question is, how much do you have to strain in order to have the system sheared? And the second question is, what is going inside the force network of the system during shear jamming, during this shear jamming? So first, the system is unjammed, then it's becoming fragile, and then suddenly it shear jams. So the details about this slow enough, 10 times, 100 times, 1,000 times slower than you are normally used to, those are published in Pulses and Grains 2021 and will be published shortly in Frontiers 2023, also including system size dependence study. So I don't have the time to go into details here. I'd rather continue with something else interesting. Now, in order to formulate this theory, which I mentioned, which I showed you some preliminary results already, we have to appreciate one more thing, and that is the jamming diagram, but in event-related form. Note that many interesting things are happening. So we have history dependence, we have slow relaxation, we have creep, aging, we have shear jamming, as I showed, and we have the jamming point, which is not a point, it's a variable. This has to be appreciated, and only if this is appreciated, then we can formulate this general theory, which includes the events, their probabilities for events, and which includes jamming, unjamming, fluid-solid transition, gas states, fluid states, and solid states, as it's so interesting for granular physics. Now let's take a look at stress versus density. We come from unjammed, low density, we compress up to a certain magnitude of density or stress, and then we go back. So the green line is going up to density density 0.68 will be fraction 0.68 and going back. And this already shows that the jamming density at the beginning, at the loading, is not the same as the unjamming density at unloading. The red is going up to a much higher density and coming back. The red dots, big dots, are the back branch. The small dots are the loading branch. Big dots are unloading. Okay, the amplitude of the difference increases. The blue lines are the 100th time of loading and unloading, and actually it becomes close to reversible. It's not exactly reversible, but it's getting close. And it's different again. So the blue line is the same system as the red system, same system loading parameters, but after 100 times, it has a different jamming density. So it's much different. Jamming density is not a constant. It's not a point, it's a variable, and that has to be taken care of. Now, left you see pressure, some of the data. The points are particle simulations, the lines are the continuum theory from 2016 actually. We had a quasi-static continuum theory at that time which worked pretty well. And the right data are experimental data. Soft hydrogel particles which confirm the loading and unloading jamming density is not the same. When we plot kinetic energy for those two cases, we see something similar as we saw under shear. There's an elastic baseline, the lower envelope of the data. There are peaks, events, which are happening under isotropic compression. So what I showed you before for shear also happens for isotropic compression, for loading and unloading with different probabilities, but that's something for further analysis. Coordination number. And then we apply the same event analysis as we did for shear. For loading, we have a lot of stress drops, as you see on the left figure. And for unloading, we have actually stress rises because we go the other direction. And the green dots in both plots are also showing the asymmetry of the probability distributions. Take the statistics and calculate the probability for isotropic events instead of shear events. We are talking now about isotropic compression. That's a different type of event than for shear events, but the statistics, the non-symmetry, the non-Gaussianness is very similar in shear and isotropic. Okay, also when you clean up the data, remove the messy part with the small events, we get the probabilities, and those we can bring into the continuum theory. And with this, the continuum theory is finished. Only the shear is not sufficient. We also need the isotropic events. Okay, and then we do the same as we did before for shear. We zoom into one event. Stress drop or stress fluctuations are happening close to jamming. Violent wiggles are happening. At high densities, the situation is slightly different, but some features like the stress drop and the kinetic energy rise and the change in modulus and the change in coordination number, they can be much bigger because the confining stress is higher, so the events can be much more violent. So this is one example. And also you see the event very isolated because for high densities, for high confining stress, the events are more isolated than for low confining stress close to compression. Okay, and all this is taken care of by the probability for isotropic plastic events. Now, this is the summary of my presentation. My presentation was about fluctuations in steady state, and we were looking closer and closer and closer. We did particle simulations and we translate things to continuum. And we deduced observed mesoscale stochastic events. Those we explain by the stochastic event probability for isotropic events, for compression, decompression, and for the shear isotropic events. I started with shear, I showed you compression later. Now, the universal continuum theory we published 2 years ago in Granular Matter, and you can read the details there. The essential pieces in the continuum theory are these two probabilities, PV and PS. So, and I showed you the microscopic origin, the mesoscale origin, the restructuring of the contact force network which goes into the continuum theory. We also did stochastic modelings. We actually did that already a few years ago before, and that's based on a master equation taking into account the probability densities, the transition probabilities from one state to the other. So that's a back reference. Thank you. So this was the recorded part of my talk, and I'm happy to take questions now anyway, and then I can switch to the second part of my talk, which is interactive. Okay, are there questions now? Because I will go into details concerning 2 of the items, so you also can wait for those, or I will refer you to the second part of my talk. Are there any questions now?
Is there? I don't see, so you can probably go to the second part, please.
Okay, thank you. And sorry, 1 or 2 of the slides had really bad sound level. I hope you could hear it anyway. I hope you could hear it throughout. So I switch now to the second part about granular matter rheology, fluid and solid like behavior state transitions, and so on. The keywords I mentioned already, so I skip over those. I want to advertise work which is related in spirit, but which was done by polymers or polymer melts. So you know the rheology G prime, G double prime for polymer melts where you have colloidal particles in. In this type of models, my colleagues, it was not my own work, it was by my colleague Wouter den Otter and Wim Briels, they have developed a numerical model for simulating polymeric melts with colloidals, and they observed shear alignment, shear migration, and such things. And from these models, they also could deduce different types of model: polymer solution, polymer melt, warm like micellar solutions, and they could deduce the G prime, G double prime as function of the agitation frequency. Okay, so this type is a micro-meso-macro model in some sense. It's called RAPID, if you are interested, and its application to polymeric systems plus particles in it, but the polymers play the big role here. Okay, so just an advertisement. The other keywords, you heard some of them through my talk, and some of them need a little bit more explanation. The states, what I refer to as state, is the state of solid, state of liquid, state of gas. And state transitions are transferring from solid to liquid, liquid to gas. I will not talk much about gas. It's mostly about solid to liquid or liquid to solid. Okay, now, one thing before I go to the details is that you always need some experiments in order to classify the system, in order to measure what is going on in the real system, not in the numerical system. I didn't talk much about experiments, but I want to refer to. Okay, now, there are state variables in a theory, and there are also state variables which are relevant for your material. And the state variables, I can plot 2 state variables in a 2-dimensional diagram. One is the confining stress, horizontal right, and the other one would be the shear rate, vertical down. Okay, and the green abbreviations and the yellow abbreviations are experimental devices which work in certain range. So GranuHeap and GranuDram work for not too high confining stress, for low and high shear rates. A tabletting simulator will work at extremely high confining stress and very high shear rates. And the classical shear testers work on this axis, tensile or compressive sheared. Okay, so these are experimental devices, and with these devices you can measure different things. In geotechnics, you are typically interested in higher confining stress. In process engineering, you are interested in lower confining stress. In tabletting, you are interested in very high confining stress and very high rates. And there are other processes to think about. Okay, so this is a reference to experiments. And unfortunately, there are many, many different experiments, and not everything, I claim you cannot get all the information which you want from a single experiment, because that one is only working in a certain range and not outside. Okay, so keep that in mind. One example of our work where we did some experiments was the tensile powder testing, and we were bringing actually the new experimental results and old experimental results together. The gray surface is a classical thing from 70 years ago, so-called the Vroslev surface, and it brings all the experimental data on this surface in the shear stress, void fraction or volume or density on one axis, on the other, shear stress on the vertical axis, density on another axis, you can call it different names, and normal confining stress on the axis to the right. And all the experimental data are fitted by this nonlinear surface, and the blue line and the red line are special cases. The red line is related to the yielding from the previous speaker, but it's also related to the initial consolidation in the soil mechanics community, or to the jamming density, as I mentioned in my previous talk. So here, with this plot, the different communities come together, but still the different communities are using different languages. I was using my language. Sorry if that sometimes was not the wording which you are used to. Okay, and this is experimental data where we brought different elements together into one theoretical best fit to the experimental data. And then if you have a best fit, you also can work with theory or compare to simulations. Okay, so that was one thing. Another thing which I will not talk about much, unless you ask me, is powders. This is a numerical model with our open source package Mercury DPM. Powders, relaxation, compaction by stress, and then sintering, where you increase the temperature, decrease the temperature, and this way increase the packing density. Okay, so we are also working on this, but I don't want to go into those details unless you ask me. Good, now I come back to the conclusion of the recorded part, and I have two details prepared. Okay, so elastic plastic, relaxation creep, granular temperature, I didn't talk much about, transients and state transitions. I showed you one or two examples only, but I didn't show you the theory which we developed for this. The other thing which I didn't show you is the stochastic model. So the stochastic model is, so to say, bottom-up. It's purely based on particles and particle modeling, and we deduce a master equation which describes the statistics on the mesoscale. We have not yet finished the step to macro scale to the continuum level. So this is bottom-up. Deterministic particle modeling. We develop a stochastic model on the mesoscale which describes the particle system. Okay, so that's option number one. If I don't get there, because I put it second, my numbering sucks. I put it second. Okay, if I don't get there, these are publications from 2015 to 2021 where this is described in detail. The option number two for continuation, and I hope I can finish that is the minimal continuum model that includes the stochastics, which I was referring to in the first part of my talk. So I would propose I continue with this unless you shout at me that I should do something else. I don't hear shouting, so I continue as prepared. So this, what I call minimal universal theory for gas, fluid, and solid, is different states, but it is not, be aware, it is not fluid-solid interaction. It is one material, and it can be in a gas state, in a fluid state, and in a solid state, and the theory should catch all the transitions also, and all the transients, by the way, and the rate dependence, and many other things. Okay, so what I call minimal is I want to have as little state variables as necessary, as little as possible, but as much as necessary. Okay, and that are 4, in my opinion, and that can be discussed, but I think 4 is the minimum you need. Okay, so the first one is density, classical density, volume fraction. Density and volume fraction are for me synonyms. I will use one or the other. And then we have elastic strain. We could use the elastic stress, but I use elastic strain, and that was inspired by Mario Liu, who developed the GSH. And okay, but it's an inspiration. And if you talk strain or stress, then you have two possibilities. The first is isotropic, not sheared, not shape changing, but volume changing. And the second is deviatoric, shear, like shear. Well, shape change, no volume change. Okay, so you can split up strain or stress into isotropic and deviatoric parts, and that are the two state variables. In 2 dimensions, that's it. In 3 dimensions, you need a third one, but I skipped that one. Okay, and then number 4 is the temperature or the granular temperature. And if you really want to make your life complicated, then you have granular temperature and temperature, both. Okay, but this is not needed for powder systems and particle systems, so I stopped with the granular temperature. The granular temperature is the kinetic energy, the fluctuation kinetic energy divided by mass, that gives us a velocity, and velocity divided by diameter gives us a time scale, a rate. So granular temperature in this definition is a rate, a 1 per time thing, and that one will show up in all rate-dependent phenomena. Okay, and universal, I call it universal because it contains all states and all transitions. At least all those which I could come up with. Maybe there are more. Good. Okay, now, GSH stands for Granular Solid Hydrodynamics. It was developed about 20 years ago and by Mario Liu, and plus means I added a few things to it, and since my expertise and what I do since more than 20 years is particle simulations, 1 plus stands for the particles, and the second plus for the particle model, and the second plus stands for the stochastic events, which are the PV and the PS, probability for isotropic and shear plastic events in an otherwise elastic system. Okay, and that's what I mentioned in the previous part of my talk already. Okay, and then you have density, elastic strains as state variables, and the granular temperature. Stress can be expressed as a function of the 4 state variables, so stress is not new, or you invert. Okay, density, elastic strain, granular temperature, I will continue with. Okay, and this is how the evolution equations look like. Time derivative of density is proportional to the isotropic strain rate and the density. Okay, that's mass conservation. This corresponds to the isotropic stress evolution. Here we write it as isotropic strain evolution, and it's proportional to the strain rate, isotropic strain rate, times 1, that's the elastic part, minus the possibility for plastic events. So the 1 stands for elastic, the PV stands for plastic. If you'd have no plastic events, you are purely elastic. If you have only plastic events, there is nothing remaining here. So 1 minus 1 would give you 0. Okay, and then you have relaxation dynamics. Tg is the relaxation rate, and it's proportional to itself. So this term, the time derivative, and this term gives you exponential relaxation, as I mentioned in the previous part of my talk. And this one is a mixed term. It connects the isotropic and the shear parts of the deformation. Okay, and then similar for the shear, time derivative, elastic, plastic, shear events. Relaxation term, plus a mixed term, which I don't spell out here. Okay, these are 3. And if you do your deformations very slowly, that's good enough. The relaxation rate will be very small. Okay, but if you want to do faster, if you want to include rate dependence into the theory, then you need also an evolution equation for this relaxation rate. Okay, and that is the classical one. And then you have something which depends on strain rate itself, and you have something which depends on the yield, referring to my previous speaker. How close are you to the yield of the material? And that also influences the so-called granular temperature, the relaxation rates. Good. Okay, so I start from the very, very basics, and that is the total energy density. So the total energy density has an elastic contribution and a thermal contribution, which corresponds to the classical thermal or to the granular thermal, and then it corresponds to kinetic energy. So we have 2. The elastic energy we can deduce from particle simulations. DEM stands for discrete element method, and it is one method to simulate particle simulations, to simulate particles. And the elastic energy density is proportional to the density, to the volume fraction. There is the coordination number, there is an effective modulus, and there's the elastic strain squared. And there's the shear strain squared with the shear modulus in the second term. Okay, and since our granular matter have no long-range forces in the simplest case, the elastic strain has to be larger than 0, otherwise the elastic energy is not defined, so it's not there. So you have a transition from non-elastic. Above a certain density, at jamming you will go to elastic, or you will activate the elastic energy. And maybe that's not all. There can be also thermal. Good. C stands for contact number or coordination number, or however you call it. And in the theory, it can be expressed as a nonlinear function with 3 coefficients, where alpha c is 0.5, delta is the elastic strain. So it's a relatively simple function which matches with the particle simulation data. So this is again the things which I added to the GSH theory because I know those things from my own particle simulations. So I intrinsically believe it. Okay, now if you take special cases, and that's what I want to do.
So if you can conclude in 10 minutes time.
Yes, sure. Thank you
very much.
for the warning. Okay, so if I want to understand a continuum theory, then I will take special cases. So the first special case is athermal. So I set Tg equal to 0, and that gives us a very simple subset of equations with which we can analyze. Or you can set the temperature to a constant that also drops out the evolution equation of temperature. But this is more related to thermal systems like glasses, as my previous speaker mentioned, or polymer melts, as I mentioned in one example before. Athermal refers more to granular materials because in many situations they are really athermal and the granular temperature can be ignored. Okay, and then you have everything in between those two, like transients and transitions. Now, there are some other cases. You can go to hyperelasticity if you set the probability for plastic events to 0. Okay, and then you can write down all the theory. It's a little bit messy equations, but it's straightforward to write down all the theory terms in the syntax which I was introducing. Okay, and then you also will get the tangent bulk moduli like compression modulus, shear modulus, and there's an anisotropy modulus also, which is due to the cross-coupling between isotropic and shear events, isotropic and shear strains. Good. So we have the total energy density, and the thermal kinetic energy, which I will not go into detail, is referring to kinetic theory. So everything here we know already from kinetic theory. It's classical thermodynamics, statistical thermodynamics, going back to Boltzmann. And in the last decades, it was extended to also add dissipation, which makes it relevant for granular matter. Okay, so from kinetic theory, we know some functions, analytical forms, which we can insert into the universal theory. Okay, and then here is the equation for the total stress, which has a shear and an isotropic contribution plus a dissipative contribution. Okay, so, and this is detailed in the paper from 21. Okay, I skipped this one. Now, if you have a continuum theory, you want to see whether it's thermodynamically consistent, so you calculate the energy and the entropy production terms due to granular and classical temperature. We skip the classical temperature because it's really orders of magnitude smaller than the granular. Okay, so we focus on granular only. You can work with the Onsager matrix. We analyze all the terms which we have in the theory. I mean, the Onsager matrix looks ugly and complicated, but actually what comes out at the end are either quadratic terms or zero terms. And this one allows you to design a theory which is thermodynamically consistent. Entropy production is larger or equal to 0. It cannot be negative in this theory. Okay. Now, special cases. Why? That helps me understand things, and also to calibrate, determine some of the parameters, some of the coefficients of the theory. Okay, so those of you who know granular material 40 years ago have talked about the classical granular homogeneous cooling state. So that's a special case. Take the granular temperature, it's decaying algebraically in a granular gas. In the gas or fluid state, the decay is algebraic, 1 over time for long times. In the elastic system, above jamming, it's exponential. So the theory makes a difference between the fluid state and the solid state. You see algebraic versus exponential decay, and this was something a surprise for me, because the exponential I didn't know. I saw it in the theory first, and then I looked at my simulations again, and actually the simulations confirm what I observe: algebraic versus exponential in a fluid or in a solid. Hyperplasticity is a special case. If I want, I can go to a limit of hyperplasticity. I can do colloids at finite granular temperature, or I can do isotropic compression, which I will do in the next minute, and I can define a large strain definition of the elastic strain. So you see, epsilon dot here is the total strain, delta or epsilon v is the elastic strain only. So that's the difference. You have total strain and elastic strain, and there's also a plastic strain, which I don't want to go into detail today. Okay, but anyway, this is the theory summarized in different words, the same as we had before. And if I go, short excursion, isotropic versus shear, I just want to highlight again, we can have a two-dimensional simplified strain tensor, isotropic, only diagonal elements. Isotropic means you are compressing from both sides, for example, in the same way. Or we can have shear, and that can be simple shear, like upper side goes to the right, lower side goes to the left, and that means compression and tension in these two directions. Or we can have pure shear, rotating this by 45 degrees, which means compression and extension in orthogonal directions also. So it's tilted by 45, rotated by 45 degrees. So we have isotropic and shear, just to make sure. If we go to the isotropic special case, a few terms in the theory drop out, and we can analyze the complete theory, all the state variables under some situations. I want to skip the details here, but I want to show you the strain rate before my time is up. This is pressure as a function of density, so related to some of the plots which I showed you before, and the different colors mean different rate. Okay, so the red line, which is actually hidden by the others below here, below the gray line, is the slowest. The magenta line, this one, is the fastest compression, and every x stands for one order of magnitude in compression rate. So the data set contains 5 orders of magnitude in compression rate. And that's what I meant when I said you have to go really, really slow to see the phenomenology which I was talking about. Okay, and you see, fast rate, very smooth. The slower you go, the sharper these plastic events get. And then you can analyze them if you have them. With the magenta, with the fast simulation, you never can see the plastic events. Pressure in logarithmic scale as a function of density, and very low pressure means we have no elastic contribution, and here the elastic contribution starts to kick in, and at very high density there's no rate dependence anymore, because the rate effects are negligible as compared to the elastic effects. Scaling it gives us pressure which is almost linear as a function of density or as a function of strain. I don't show the strain here. Okay, but there are these wiggles, there are these hiccups, these plastic events. A straight line would correspond to elastic, but everything which is not on a straight line is plastic. Okay, and this is the bulk modulus which we deduce, and the negative drops are the plastic events. For different rates, we do observe the same bulk modulus, and we get different information during the plastic events where the bulk modulus plastic event is not elastic, so the bulk modulus is not defined here. Good. So then you can play the game with the theory and with the simulations. I only show you the theory here. You can compress a bit, and then you can do small amplitude cyclic loading, ratcheting, for example. This is something, and you can measure the different densities which are involved in the system and their evolution. So the theory is complete in that sense. I can apply every boundary condition I want, and the solver will give me the data. Okay, so pressure, coordination number are results from the theory, that are the lines, and then I can compare them to DEM simulation. I showed this one already, and we did the quasi-static, TG equals 0, we did the comparison already in 2016, but at that time we didn't have a theory which contains the transients and the non-elastic states and the rate dependence. You can go further. I don't want to go into details here, but this is logarithmic long-term aging. I only give you the keyword, I don't tell you the details. This is the proof or the confirmation that the jamming density or the solidification density is a function of history. For different history, you get different densities in this gray area. So the consolidation density, the jamming density, however you call it, I do not call it yield density. The jamming density is a function of history. The yield density is another story. That's not the same thing. Okay? And you can do models with different friction coefficients, for example, just to mimic different types of real materials. And they also scale in the same way as the previous data, which were actually frictionless. Okay, and some interesting things are going on when you zoom in here. Dynamics is much more important close to jamming than for higher densities. Okay, and then you can do shear. I showed you the shear results already, so I don't want to repeat those, but I want to show you an animation of a shear event. Shear here is pure shear, so we have compression vertically and extension in one horizontal direction. The color means how many numbers, how many contacts has a particle. So blue is 0 and yellow and red are high numbers. So it starts again from the beginning. At a certain point we get fragile, so a lot of bluish particles, and then it jams here. Elastic. Elastoplastic, I should say. Okay. Now, this is the end of this part of the talk. Unfortunately, I didn't get to the stochastic model. I was not fast enough to tell you everything I could tell you, but I want to stop here then. This is a didactical thing. I want to stop here with, give me a second, with a conclusion. Where is it? I showed you the minimal universal theory, particles continuum for all states, gas, fluid, solid. I showed you a few examples, and the probability for plastic and elastic events. That one includes the mesostochastic events into the macro theory. So that's what I showed you now. Oops. That what I showed you now is a macroscopic theory where I phenomenologically include stochastics, mesoscale, based on particle simulations. So that was the top down. And if I would have another 20 minutes or 10 minutes, I could tell you something about the bottom up approach, where we built a stochastic theory. We have built a stochastic theory based on particle simulations. That one I'm still working on, because here the connection to the macroscopic scale is missing yet. So what I showed you here is we have the microscale, the mesoscale, and the macroscale combined together in a macroscopic theory with all these features. Thank you.
Let's thank Stefan for the wonderful talk. So, is there any question? You can have question from both the parts. Well, if not, then let's thank Stefan once again for the wonderful talk. Thank you very much. Thank you.
Okay, and I understand your conference comes to an end now.
Yes.
So
yes.
I hope I didn't keep you from finishing your conference.
No, we were absolutely on time. Thank you.
Thank you.
Thank you. Thank you
Bye.
very much. Bye. Yeah. So with this, we come to the end of Fracmeet 2024. I will now request Professor Debayan Chakravarti for just to conclude and vote of thanks.
Okay, so I hope I'm audible to everyone.
Debayan, just yeah, they're there.
Okay.
Little side.
Little bit
This side?
Yeah, because they're on the.
Oh, I see. Okay.
They're watching.
I see. Okay. Okay, so I'm audible, right? Okay, so it is my pleasure to deliver this vote of thanks on behalf of the other organizers, Professor Purushottam Ray from IMSC Chennai and Professor Shubhadeep Roy from BITS Hyderabad. So first and foremost, I would like to thank all the speakers for the fantastic talks spread over the last 4 days, and also the students for their poster presentations. So, so the idea of Fracmeet has always been to encourage stimulating discussions among the participants, particularly among the young participants and the world leaders, and we witnessed plenty of that in this year's Fracmeet. So please, one round of applause. So it's your presence and active participation which made Fracmeet truly a memorable event, filled with positivity and excitement. So we express our utmost gratitude to the Director of Math Science, Professor Ravindran, for his support and encouragement. We are extremely thankful to the Department of Atomic Energy, Government of India, for providing the financial support through the Soft Matter Apex project, which enabled us to organize Fracmeet. So a big round of applause for that. So I'm very thankful to the other principal investigators in the Soft Matter project, Professor Satyavani Vemparala, Professor Rajesh Ravindran, Professor Arnab Pal, and Professor Pinaki Chaudhary for their constant support and encouragement when we were planning Fracmeet. So please clap for them. So we express our thanks to our administrative team supervised by our registrar, Mrs. Vinayalata, our administrative officer, Mrs. Indra, and ably supported by Sadhana and Maurya. So they worked tirelessly during the months leading up to Fracmeet to ensure that we procure all the necessary approvals from the Department of Atomic Energy and the different ministries. So thanks to all of them. So we are very grateful to Mr. Johnson, our guest house committee, the housekeeping staff, for ensuring that you have a comfortable stay at the Institute during Fracmeet. We also thank Mr. Johnson for liaising with the DAE Nodal Center at Pallavaram, where the students and the postdoc participants were housed during the days of Fracmeet. So we thank the hospitality and support staff at Hotel Jinja and Mr. Prem Kumar for coordinating seamlessly with the IMSC administrative staff to ensure that our speakers have a comfortable stay. We thank Mr. Shankaran and Indra Madam once again, who coordinated with Palmer and Laurie to book the tickets for some of our invited speakers. So the local transportation services were provided by Palmer Travels. We thank them for organizing the drop-off and the pickup services from the airport and the hotel, and also Mr. Johnson once again for coordinating with them. So we also thank the media team of Ms. Gayatri and Shiva, who are sitting inside, who worked tirelessly during Fracmeet to ensure that the recording and the live streaming of talks were carried out with minimal disruptions. We also thank the IT team, comprising Mr. G. Srinivasan, Mr. Ravinder Reddy, and Mr. Nagamaleshwara Rao. We thank the IMS Electrical, Civil, the housekeeping and the security staff for their tireless efforts. And as you will appreciate, providing catering services for an event of this scale spanning 4 days is a humongous task. So we thank the IMSC catering team, consisting of Krishna Balaji, Rajkumar, Munuswamy, Amarendra, and others. So please a big round of applause for the catering staff. We also thank Mr. Johnson and his team for arranging the stationery and ensuring the badges and the posters were printed on time. And last but not the least, we thank all the student volunteers. So please raise your hand as I call you. Reshmi, Tahir, Ravindranath, Vishwajit, Hitesh, Shubhasri for all the hard work and the support. Another big round of applause. They did all the hard work. And finally, I thank all of you once again for making Fracmeet 2024 a success, and we will see you in the next edition. Thank you.
Thank you.
Yeah.
Thank you.
Thank you.
Okay.
Okay, yeah.
Yeah. Okay.
So Alex, what's his name?
Alex is drop.
Yeah, I think.
Bag. Oh, Raman is drop. Bag.
Oh. So you can tell